Hi, hello, vanakkam, and welcome back to yet another episode on your favorite Little Slaw YouTube channel. And today, this is our next interview question. And today, we are going to dive into another critical performance testing interview question that you are almost guaranteed to face in your interviews. So, we're going to discuss when exactly you should capture the thread dumps during a load test. And this is not just theory, I'm going to share real world scenarios and a few practical examples from actual projects that will help you answer this question like a seasoned performance testing professional. By the end of this video, you'll know exactly when to capture thread dumps, how to do it, and why timing matters so much. And let's get started. So here is the question that we are tackling today. When should you capture a thread dump during a load test? And this is a practical question that tests not just your theoretical knowledge, but your real world experience with performance testing because interviewers want to know that you can actually troubleshoot performance issues in production like scenarios. So let's break down the complete answer scenario by scenario. So the first scenario is when or where you should capture a thread dump is when response time suddenly spike. So let me explain what I mean. So during your load test, you are monitoring response times and they're running smoothly. And let's say around 200 milliseconds on average. So then suddenly, without any changes in load, they jump to 2000 milliseconds or even 5 seconds, right? And that's your trigger to capture the thread dumps immediately because when this happens, you're looking for threads that are in a blocked or waiting state. And now let me give you a real example from a project I worked on because we were load testing an e-commerce application with 500 concurrent users. Everything was running fine. Response times were around 300 milliseconds. Then suddenly they spiked to 5 seconds. I immediately captured three thread dumps at 10-second intervals. So what did I find? You'll be surprised or shocking to know that 80% of the threads were blocked, all waiting for database connection pool resources. The connection pool was only configured for just 20 connections, which was clearly insufficient. So we increased it to 50 connections and the response times immediately dropped back to normal. So this is a perfect example of how thread terms help you pinpoint the exact bottleneck. And moving on to the second scenario. So the second scenario is when throughput drops. And this is really interesting because your load is constant. You're not reducing the number of virtual users, but your transactions per second just starts declining. For example, you might expect 100 transactions per second based on your load, but you're only seeing 30 or 40 TPS or transactions per second. And this is a red flag that something is causing contention or blocking in your application. So let me share another example. So in a banking application load test, we maintained 1000 virtual users throughout the test. So initially we were getting 150 transactions per second, which was really great. But after about 10 minutes, the TPS, the transactions per second, dropped dramatically to just 45 transactions per second, even though the load was unchanged. So we started to capture the thread dumps, and here is what we discovered. Multiple threads were waiting for a synchronized block in the transaction logging module. Essentially, all these threads were queuing up to access a single piece of code that could only be executed by one thread at a time. So what is the solution for this? So we refactored the code to use concurrent data structures instead of synchronized blocks, and the throughput improved by 200% because thread dumps made this diagnosis possible in minutes rather than hours or days of investigation. And moving to the next interesting scenario, that is high CPU and low TPS. This is a very common one. This is what I call the performance paradox because high CPU utilization but low transactions per second. And this is actually one of the most common issues that you will encounter in performance testing. And here is what it looks like. Your CPU is running at 95 or even 98% utilization. And you would think the application is doing a lot of work, right? But when you check your transactions per second, you're only getting 20 or around like 30 TPS. And something is clearly burning your CPU cycles without producing results. In thread dumps, you are looking for threads in runnable state that are doing excessive computation or they might be stuck in some tight loops. So let me give you a real example. So we are testing a REST API service and we saw exactly this pattern, that is around 98% CPU usage, but only 25 requests per second. It might be confusing, right? So the business was concerned because they needed to support at least 200 requests per second in production, but we were actually doing some 25, which is like one eight of it. So when we analyzed the thread dumps, we found that multiple threads were executing a poorly optimized regular expression pattern, which is matching the algorithm. And every single request was running this regular expression pattern against the large strings, and it was consuming massive CPU cycles. So what did we do is we optimized the regular expression pattern and implemented caching for frequently matched patterns. And after doing all this, the result was the CPU dropped to 45% and TPS jumped to 200. So the thread dumps showed us exactly where the CPU was being wasted. And now the next one, the scenario 4 and 5, I would say, because they are unresponsiveness and errors. So let's talk about two critical scenarios when the application becomes completely unresponsive and when the error rates increase. First thing, the unresponsiveness. This is when your application just stops responding to requests entirely because everything freezes. And in this case, you need thread dumps immediately because you are likely dealing with either deadlock or all threads stuck in a waiting state. I'll give you a real deadlock example here. So we were testing a payment processing module, and after 15 minutes under load, it became completely unresponsive. Not slow, it's completely frozen. We could not click on any items, we could not click on any buttons, or even we cannot type anywhere anything in the screen. So what we did is we captured a thread dump, and there it was. It was a classic deadlock. Thread A was holding lock number 1 and waiting for lock number 2. Thread B was holding lock number 2 and waiting for lock number 1. So neither could be processed, and this is exactly what thread dumps are designed to catch. So the fix was simple. Once we identified it, we reordered the lock acquisition sequence to prevent this circular dependency. And the second scenario is increasing error rates, because when you suddenly see a spike in HTTP 500 errors or timeout exceptions, the thread dumps can reveal whether it's due to thread pool exhaustion or resource starvation. Maybe you have run out of available threads, or maybe threads are stuck waiting for external resources like databases or web services. And moving on to the best practices, the three dump rule. So now here is a critical best practice that you should always mention in interview. Always capture three thread dumps at 10 to 15 second intervals. Never just capture one. So why three dumps? Why three thread dumps? Or why three snapshots? Let me explain. So firstly, it will help you to confirm the patterns. One single thread dump might show just a temporary state. Maybe a thread was momentarily blocked and then released. So three dumps lets you see if the issue is persistent. Secondly, it helps you to track the progression, because you can see if threads are actually moving through their execution or if they are truly stuck. If you see the same threads in the same state across all three dumps, you know you have a real problem. And third, it's essential for identifying deadlocks. A persistent blocked state across multiple dumps is a strong indicator of a deadlock situation. So the recommended approach here is you have to capture one at t equals 0 seconds, dump 2 at t equals 10 seconds, and dump 3 at t equals 20 seconds. So this interval is long enough to see the meaningful state changes, but short enough to capture the issue before it potentially resolves itself. And then the slider 8, where I'll tell you about the technical commands. So now in your interview, you want to show that, or you want to at least write and show them that you don't just know when to capture thread dumps, but also how to do it. So let me share the actual commands. So the most common method is using JStack. So you simply run JStack followed by the process ID and redirect the output to a text file. So for example, JStack 12345 and redirect to thread dump 1.txt. On Linux or Linux systems, you can also use the kill command with the -3 signal. So this sends a signal to the JVM to print a thread dump to a standard output. So the more modern approach is using J command, which is J command process ID, the thread.print redirect to your file. And here is an important one for today's world. So if you're working with containerized applications in Kubernetes, you would use kubectl execute to run JStack inside the container. But here is the pro tip I want you to mention in your interview. In real projects, you should automate this process. For example, you can say something like, in my previous project, I scripted 3 dump collection triggered by monitoring thresholds. So when response time exceeds 3 seconds, it automatically captured 3 dumps at 10-second intervals, and this shows initiative and real world thinking. So let's summarize. So when you should capture thread dumps during a load test. So a quick summary. Number one, when response time spike, when they jump significantly above your baseline, that's your signal. Number two, when throughput drops, when transactions per second decreases even though your load is constant. Number three, when you see high CPU but low TPS, this performance paradox indicates wasted CPU cycles that thread dumps can help identify. Number four, when the application becomes unresponsive, this often indicates deadlocks or stuck threads. And number five, when error rates increase, spikes in failures or timeouts, that thread dumps can help diagnose. And the golden rule is always remember capture 3 thread dumps at 10 to 15-second interval. This confirms patterns and help you distinguish between temporary states and real persistent issues. So this approach has saved me countless hours of troubleshooting in production incidents. And finally, there you have it. You have now a complete interview ready answer to when should you capture thread dumps during a load test. But more than that, you have real world examples and practical knowledge that will make you stand out from other candidates. So when you can talk about specific scenarios, actual metrics, and real solution, interviewers know you are not just a book smart, you have genuine experience. Remember, the key is to speak naturally, share these examples as if they are your own experiences, and show that you understand both the technical details and the practical applications. You've got this. Good luck with your interviews, and I'll see you in the next video. Until then, it's bye bye from Shanmugam and your favorite Little Salah YouTube channel. Take care and bye bye. Hi, hello, vanakkam, and welcome back to yet another episode on your favorite Little Salah YouTube channel. So today we are going to cover another fundamental question that comes up in almost every performance testing interview. So we're going to discuss the different thread states that you will encounter in a thread dump, and this is absolutely essential knowledge because understanding the thread states is the foundation of thread dump analysis. And I'm not just going to give you definitions, I'm going to show you real examples and explain what these states means in real or in actual performance testing scenario. And let's dive in. So the question here is, what are the different thread states in a thread dump? So this question tests whether you actually understand how to analyze thread dumps, not just whether you have memorized some definitions. So what the interviewers does is they want to see that you can interpret what's happening in a running Java application. So let's break down each thread state with a real world context. So in a JVM thread dump, you will encounter 4 common thread states. The first thing is runnable, and then we have blocked, waiting, and timed waiting. So each of these states tells you something different about what your application is doing at the moment in time. And here's the critical part. So it's not just about knowing the definitions, because you need to understand what distribution of these states is normal versus what indicates a performance problem. So you need to know the difference. You need to know the understand the difference between these, like what is normal and what is a problem, performance problem basically. So for example, having threads in a waiting state is not necessarily bad. It could be just idle worker threads, which can be waiting for some tasks. But having 80% out of 100, like I'm telling, 80% of your threads in a blocked state. So what does that mean? So that means you have a massive red flag indicating there is some serious synchronization issues. So understanding these states will make the difference between guessing a performance problem and actually diagnosing them with the precision, right? So let's move to the next slide. So let's start with the very first one, my favorite, that's the runnable state. So a thread in runnable state is either actively executing on the CPU or ready to execute and waiting for the CPU time. So think of it like someone who is either currently working or standing in line who is ready to work. So now here is what this actually looks like in a thread dump. So you will see. So this in fact is actually a real time error, like real time thread state, which so where you will see like java.lang.thread.state runnable, which is followed by a stack trace showing what the thread is executing, right? So let me give you a real example from a project I worked on. So during load testing of a data processing API, I noticed 85% CPU utilization with 200 threads in runnable state. So when I analyzed the thread dumps, these threads were executing some complex mathematical calculations and some JSON parsing operations. So by viewing this, I mean, 200 threads, 85% CPU utilization, and again 200 threads in runnable state. So what is my analysis on this? So this was actually normal behavior, right? The threads are actively doing some CPU intensive work. The high CPU usage was expected and appropriate for the workload. And this is what the runnable threads should be doing. But here is the important difference or the important distinction which I noticed. That is, runnable can be good or bad. It's good when threads are processing the business logic and calculations. It's bad when you have hundreds of runnable threads stuck in IO operations or like infinite loops. So you need to look at the stack traces to understand the difference. So now let's move on to the next one. That's the blocked state. So this is one of the most important states to understand, because a thread in blocked state is waiting to acquire a monitor log that is currently held by another thread. Essentially, it's like saying like I need this resource, but someone else has it locked or someone else is holding it. So I'm stuck waiting. So this is something like that. So in a thread dump, you will see the same way that you see here, like java.lang.thread.state blocked on the object monitor, and it will tell you which lock it's waiting for and which thread currently holds that lock. And I would suggest you just even you can by heart this for your interview as well. So let me share a real world example that perfectly illustrates this. So I was testing an e-commerce checkout service, and I was experiencing some 10-second response times under a load of 500 concurrent users, and that's completely unacceptable for a checkout process. So when I capture the thread dumps, so here's what I found. That is 380 out of 500 threads, that's 76% were in blocked state, and they were all waiting for the same lock on the inventory update method. So what was the root cause of it? So when I was doing the root cause analysis, I found out that there was a synchronized block around the entire inventory check, and the update operation was creating a massive bottleneck. So only one thread at a time could execute this code, so everyone else had to wait. So the solution was, which I suggested to the development team, is to refactor it using a read-write lock, because this read-write lock will allow the read operations to proceed concurrently. Multiple threads could check inventory at the same time, and all we needed are an exclusive lock for actual updates. And the response time dropped from 10 seconds to 400 milliseconds. So after doing all this refactoring, we only needed an exclusive lock for actual updates. So the response time, so as I expected, it dropped from like 10 seconds to 400 milliseconds. So the critical rule, which I always mention in interviews, is like large number of blocked threads. Anything over 30% almost always indicates synchronization issues and severe performance bottlenecks. And this is a red flag that you need to act on immediately. And moving on to the next state, that's the waiting state. So this is the third state. So a thread in waiting state is waiting indefinitely for another thread to perform a specific action, like sending a notification or completing its execution. So in thread dumps, you will see java.lang.thread.state.waiting. So the one that you see here, followed by methods like object.wait or blocking queue.take. So let me tell you a real example which I have worked on. Um, that will show you like why understanding the waiting state matters, because we had a message processing system with like 50 worker threads, but it was only processing 10 messages per second despite having 1000 messages sitting in the queue. So something which I found was like, it was very clearly, it was very wrong. So what I did is I did a thread dump analysis, and that revealed that 45 threads were in waiting state on the blocking queue. And in fact, you won't believe there were like thousands of waiting threads were in the waiting queue in some other scenario. But this scenario, like I had like around 45 threads, which I always normally use for the interviews, which are waiting on the blocking queue.take method. So they are waiting indefinitely for messages to appear in the queue. So the root cause was, it turned out to be that the producer thread, the one which is responsible for adding messages to the queue, had crashed silently. So the worker threads were waiting indefinitely for messages that would never come. So our solution was twofold. So first, we added producer health monitoring with automatic restart. And second, I implemented a timeout based approach instead of indefinite waiting. So the threads could detect and recover from this kind of failure. So the common causes of waiting state are like what that could include like object.wait, thread.join, blocking queue.take, because these are all scenarios where one thread is waiting for another thread to do something. And now let's move to the other one, that is timed waiting state. So this is a fourth state which is timed waiting. So this is similar to waiting, but there is a difference. The thread is waiting for a specified amount of time before it gives up or it takes an alternative action. So you will see java.lang.thread.state timed waiting or timed waiting in thread dumps, so which is followed by methods like thread.sleep or object.wait with the timeout parameters. So let me share an example which involved connection pool timeouts. So I had a REST API which is experiencing intermittent 30-second delays during peak hours. It's not a permanent or it's not a definite one, it's an intermittent kind of one. It's completely random, and it was like very frustrating to diagnose, because sometimes when we were like demoing it to the developer, it was working fine, and then when we were testing it from R&R, when we were trying to reproduce it from R, it was like throwing 30-second delays. So I started to do the thread dump analysis, and I actually showed like 120 threads in timed waiting state and all waiting in the database connection pool with a 30-second timeout configured. So just imagine how frustrating it was. So what was the root causes? Our connection pool size was only 20 connections, but the peak load required 150 concurrent database connections. The threads were literally waiting up to 30 seconds just to get a database connection before timing out. So the solution involved three actions. So firstly, we increased the pool size to 100 connections. Second, we reduced the timeout to 5 seconds with proper error handling, which is better to fail fast and than making sure that we wait for like 30 seconds. And thirdly, and most importantly, we identified and fixed several slow queries that were holding connections for too long. So the common causes of timed waiting, which includes thread.sleep, object.wait with the timeout, and connection pool waits, and any operation with a time limit. And finally, a quick comparison chart. So let's look at a quick comparison to help you remember when each state is normal versus when it indicates a problem. So runnable is normal when processing business logic and calculations. It's a problem when you see threads stuck in infinite loops or high CPU with low throughput. Blocked is normal for brief blocking during synchronization. It's a problem when 30% or more of your threads are blocked. That's a synchronization bottleneck. Waiting is normal for idle worker threads waiting for tasks. It's a problem when all workers are waiting but you have a full queue that indicates producer failure. And timed waiting is normal for scheduled tasks and polling intervals. So it's a problem when many threads are timing out on resources. That's pool exhaustion. The key is understanding the context. So the same state can be perfectly normal in one scenario and a critical issue in another scenario. And moving on to the ninth slide. So the critical insights that you can use to impress the interviewers are the 30% block rule. So when more than 30% of your threads are in blocked state, you have a serious synchronization problem that requires immediate attention. So this is not a guideline, so it's a kind of a red flag. So now here is how to analyze thread states in practice. So I normally follow five-step process. So the first step is count the threads. So count the threads in each state and look for unusual distributions. So if 70% of threads are blocked, that's unusual. Step 2, for the blocked threads, identify which lock they're waiting for and more importantly, who holds it. So this tells you where the bottleneck is. And step 3, for waiting threads, determine if it's expected behavior like worker pools or problematic like hung processes. And then the step 4, for timed waiting threads, look for timeout patterns that indicate resource exhaustion. And step 5, compare across your 3 thread dumps to confirm that issues are persistent and it's not just temporary states. So the pro tip, which I always mention, so don't just look at thread states in isolation. Analyze it. Yes, analyze the distribution of states and rate the stack traces to understand what the application is actually doing, and that's what separates good performance testers from great performance testers. And moving on to the last one, the summary. Um, so let me quickly summarize the four thread states. So runnable is the thread is executing or ready to execute. So look for CPU intensive operations or input output waits in the stack traces. Blocked is waiting for a monitor lock held by another thread. Remember, 30% or more blocked threads means you have synchronization issues that need immediate attention. Waiting indefinitely for another thread's action. This is common in worker pools and task queues, but verify it's intentional. Timed waiting is waiting for a specified time. Check for timeout patterns that might indicate resource exhaustion. So here is what I want to remember for your interview. Don't just memorize definitions. Explain what each state means in real performance scenarios and share examples like I did of how you have used this knowledge to solve actual problems, and that's what makes you stand out. And finally, that's it. You are now ready to ace the question about thread states in thread dumps. So you understand all four states: runnable, blocked, waiting, timed waiting with real world context and practical examples. Remember, interviewers want to see you that you can analyze, not just define. So when you can explain what a distribution of thread states, that tells you about an application's health, and when you can share specific examples of how you have used this knowledge to diagnose performance issues, you demonstrate genuine expertise. So practice explaining these concepts naturally, and you will absolutely crush this question in your interview. So good luck, and I'll see you in the next video. Until then, it's bye bye from Mr. Shanmugam and your favorite Tutorials Law YouTube channel. Take care and bye bye. Hi, hello, Vanakkam, and welcome back to yet another episode on your favorite Tutorials Law YouTube channel. And in the last few days, we are seeing about the thread dump related interview questions, and in fact, we saw about what is a thread dump and what are the scenarios that you look for thread dumps, and how do you take thread dumps, and what are the various states of thread dumps. So all of these were discussed in the previous sessions, and I believe they are very useful for you. And moving on to the next topic. So today we are going to tackle an advanced performance testing question that really separates junior testers from senior or experienced engineers. So we're going to discuss how to identify CPU issues using thread dumps. So this is a critical skill because high CPU usage is one of the common performance problem that you will encounter in production or in any other systems. So I'm not just going to give you theory. I'm going to walk you through a real world example and show you the exact commands to use and give you a complete investigation methodology that you can apply immediately. So let's jump in without any delays. And moving on to the question, so how do you identify your CPU issues using thread dumps? So during your load testing, right? Or obviously not during your load testing. So anytime it is. So how will you identify your CPU issues? So this question tests whether you understand the complete diagnostic process and not just the thread dumps in isolation, but how to correlate them with operating system metrics and profiling tools to get the full picture. So the interviewer's perspective would be like they want to see that you whether you have a systematic approach to troubleshooting and not just some random guessing kind of things. So moving on to the third slide. So when investigating the CPU issues, I normally use a three method framework combined with correlation techniques. So the three investigation methods are: first, looking for threads in runnable state. Secondly, and in fact, we discussed about what a runnable state is, and we discussed about what the other states are in the previous video. And secondly, finding the repeated stack traces across multiple thread dumps. And thirdly, identifying the threads which are stuck in computation heavy loops. So these are the three investigation methods that I start with. But the critical principle that many of us miss, I mean, even I would have missed, I have missed it previously. That is, thread dumps alone only tell you that where the CPU is being spent, but they again they show you like which code is executing, but you need to correlate that with the operating system level metrics and with profilers to get the complete picture and to confirm your findings, like whatever you have found so far. So think of it this way. So thread dumps are like taking snapshots of a busy kitchen in a restaurant. So you can see who is cooking, but the OS metrics tells you which stove is burning the most gas. And the profilers are like time-lapse photography, which shows you exactly how long each dish takes to prepare. So this combination of technique is what makes the difference between guessing and actually solving the CPU problems. And moving on to the next slide. So the method one, as I told you, so we got three methods out of that. The method one, which is looking for threads in runnable state. So here is the pattern that you need to understand. So when CPU usage is high, let's say 80% or above, you capture three thread dumps and count how many threads are in runnable state in each dump. Because in a normal scenario, you would expect maybe 10 to 20% of threads to be runnable at any given moment. So these are threads which are actively processing the request. But in a CPU issue scenario, you will see 60 to 80% of threads in runnable state simultaneously, and that's your first red flag. So let me share you a real example. So we had a financial reporting service, a financial application that was hitting 98% CPU during month-end processing. So the application became completely unresponsive. When I say completely, yes, it's completely unresponsive. So users could not even log in. So I captured three thread dumps at 10-second intervals, and what I found was really shocking, and even the entire team was shocked, that 85 out of 100 threads were in runnable state. When I looked at the stack traces, I saw they were all executing the same method, which is like formatting currency. I think that was the method which I remember. So here is what was happening. So the format currency method was using an extremely inefficient regex, regular expression pattern, to format the currency values, and it was doing this 500,000 times, like just once for every transaction in the monthly report. So the solution was very simple, but it had actually a massive impact. So we replaced that regular expression with number format.get currency instance, which is specifically designed for currency formatting. And because of this change, the CPU dropped from 98% to 25%. And you won't believe that, yes, it happened. And the report generation time went from 15 minutes down to like less than 2 minutes. So this is actually a perfect example of how counting the runnable thread points you to the problem code. And moving on to the next one, my favorite method, that is repeated stack traces. So finding repeated stack traces across the dumps. So here is why this technique is so powerful, and my favorite is, if you see the same exact stack trace appearing across multiple thread dumps that are like 10 to 15 seconds apart, it means those threads are stuck executing the same code again and again. So it's a smoking gun for CPU intensive operations. So let me walk you through a real investigation. So we had a REST API service which is experiencing 95% CPU, but only processing, like it was only processing, the CPU was only processing like 50 requests per second. So this was far below than our expectation, or far below our expected capacity of like 500 requests per second. So what I did is I captured three thread dumps, and here is what I noticed: the same 30 threads showed identical stack traces in all three dumps. So at t equals 0 seconds, thread 12 was in XML parse.parse. So at t equals 10 seconds, still in XML parse.parse, and t equals 20 seconds, still in the same method. So this told me immediately that XML parsing was taking at least 20 seconds or more per request. So when I investigated the code, and I even discussed that with the development team, so I discovered that the XML schema validation was happening on every single request, and it was not caching the schema. It was actually parsing a 5 MB schema file from scratch every single time. So each validation took like 8 to 10 seconds. So what was the solution I gave them is I cached the parsed schema at application startup, and because of that the CPU dropped to 20% and throughput jumped to 600 requests per second. Actually, it was exceeding our target, it was exceeding our SLA as well. So now the tip here is, I always mention in interviews, I use diff tools or simple scripts to compare thread dumps side by side. So if I see the same thread ID with the same stack trace across all three dumps, I know exactly where to focus my optimization efforts, and it's not a guessing game. And then the third one, the computation loops. So it will be helpful if you want to identify threads which are stuck in computation heavy loops. So when you analyze the stack traces, you're looking for specific patterns that indicate inefficient algorithms, right? So things like threads stuck in tight while or like for loops. So the recursive methods which are appearing multiple times in the stack, sorry. So the string manipulation methods inside the loops, the collection operations on the large data sets are the regular expression pattern which are matching in the repetitive code. So let me share you one of my favorite examples because it perfectly illustrates how bad the algorithms create CPU problems and how important the designing is. So we had a user search feature that caused 100% CPU spikes, which lasted like for 30 to 40 seconds. And whenever someone used it, users were complaining, and the business was considering disabling the feature entirely because they don't want to like get bad will from the customers because of this particular transaction. So when I analyzed the thread dump, here is what I saw. The stack trace showed an outer loop which is iterating through like 10,000 users and an inner loop using array list, which contains to check against 50,000 criteria items. So let me do the math for you. So 10,000 users times 50,000 items, which equals 500 million comparisons, and array list dot contains is an 0 of n operation. So each comparison has to scan through the entire list. So this was a classic 0 of n squared algorithm problem. So the code was doing 500 million operations every time when someone searched. So the solution was actually straightforward. We converted the criteria list from array list to a hash set. So hash set that contains is 0 of 1, which is a constant time. So regardless of size, this changed the algorithm from 0 of n squared to 0 of n, and the search time dropped from 35 seconds to zero point 0.8 seconds. So some of the common CPU heavy patterns I always look for: string concatenation in loops, using string builder instead of that, and array list dot contains in loops where I use hash set, and instead of creating unnecessary objects inside tight loops, and compiling regular expression patterns repeatedly instead of caching them. So these are some of the CPU heavy patterns which I normally look for. And then moving on to the seventh slide, which is correlating with the OS metrics. So let's talk about correlating thread dumps with the operating system level CPU metrics. And this is where you move from I think this code is a problem to I know for certain that this specific thread is consuming the CPU. So here's why this matters. So the thread dump shows you what code is running, but the OS metric shows you which specific threads are actually consuming CPU at the operating system level. So let me walk you through the exact process I use. So step one, I use the top command with the -h flag on Linux to see the thread level CPU usage. The command is top -h-p, which is followed by this Java process ID. So this shows me individual thread IDs and their CPU consumption. So for example, I might see thread ID 25,432 consuming 787% CPU. And the step two, I convert that thread process ID to hexadecimal because the thread dumps use hexadecimal notation for native thread IDs, and the command is, as you see here, the printf %x/n, so which is followed by the thread ID. So 25,432 becomes 6358 in hex. And step three, I search for this hex value in my thread dump. So I'm looking for TID equals 0x6358. When I find it, boom, I've got the exact thread and the exact stack trace consuming all that CPU. So let me give you a real example. So we had an application which is showing 80% CPU, but we were not sure which component was responsible, using top -h. So I found the thread like 31,245 consuming 78% CPU. I converted it to a hex 0x7a0d, searched my thread dump, and found it was the cache refresh thread. So the cache refresh was running every 5 seconds with an inefficient algorithm. So as I told you, algorithm is always very important, and the designers have to be very careful with that. So we optimized that specific cache refresh logic, and the problem was completely solved. So without the OS correlation, we would have been just guessing like which component was the culprit, but instead the guessing will not actually work every time, like all the time. And then the profilers slide. Yes. So let's talk about using profilers for deeper analysis. So I use two main tools, and these are my favorite tools. I always have that with me, and they are the Java Flight Recorder and Async Profiler. So Java Flight Recorder, or JFR, which I call it as, is built into the JVM, and it has minimal overhead, so just less than 1% performance impact. So I can safely use it in production as well. So that's why I told you it's my favorite tool. So here's how I use it for CPU issues. So I start a recording with J command process ID jfr.start with the duration of 60 seconds. Then I dump the recording and analyze it with JDK mission control. And this shows me hot methods, like which specific methods consuming the most CPU, the flame graphs showing call hierarchies and thread CPU usage over time. So when I use it, and after thread dumps identify the problematic code area, I use JFR to get precise CPU time attribution down to the method level and see the execution patterns over time. And the async profiler is my go-to for production profiling with beautiful visualization. So that's the difference between the JFR and the async profiler. So it can profile both Java and the native code. The command is very simple, like just add profiler.sh minus d 60 minus f cpu minus flame graph.html followed by the process id. So this will actually generate an interactive flame graph that shows exact CPU time per method, the complete call stacks and hard code paths visualized. So in a real example, I would say that in a microservice experiencing CPU spikes, the asynchronous profiler's flame graph revealed that 65% of CPU time was spent in JSON serialization. So we switched to a more efficient serializer and reduced CPU by 60%. The flame graph made this obvious in seconds. So here is when to use each tool. So thread dumps for quick diagnosis with zero setup and JFR for detailed analysis with low overhead. The async profiler for production profiling with beautiful visualizations and native code profiling. And moving on to the next one, the complete process slide. So let me give you the complete CPU investigation process that I follow. This is what you should present in your interview. So step one, detect the issue. You can see CPU above 80%, low transactions per second or slow response times. Step 2, capture 3 thread dumps at 10 to 15 second intervals. Step 3, analyze thread states, count runnable threads and look for high percentages, that is 60% or more is concerning. Step 4, compare the thread dumps. So find repeated stack traces that indicate stuck code. Step 5, identify patterns, look for loops, regular expression operations, collection operations, inefficient algorithms. Step 6, correlate with OS metrics. Use top minus h to find the high CPU threads and match them with your thread dump using the hex conversion technique. Step 7, profile if you need to do it. So use JFR, my favorite tool, or you can use even asynchronous profiler to get the method level CPU attribution and detailed evidence. Step 8, fix and verify. So optimize the code, retest under load and confirm the CPU reduction. And my interview power phase to you is, you can always tell them that I don't rely on any single tool. Thread dumps give me the initial direction, but the OS metrics help me pinpoint the exact threads, and profilers provide the detailed evidence which I need to convince developers to optimize the specific code path. So this shows you understand that it's not about knowing one tool, it's about combining multiple techniques to build an airtight case for the problem and the solution. And there you have it. You now have a complete professional methodology for identifying CPU issues using thread dumps. So you understand the 3 core investigation methods. You know how to correlate that with operating system metrics, and you can use profilers to get detailed evidence. So most importantly, you can present this as a systematic reproducible process, not just some random troubleshooting. So when you combine thread dumps, OS metrics and profilers with specific examples and measurable results, you are going to demonstrate the kind of expertise that companies are looking for. So practice explaining this methodology naturally and you will absolutely ace this question in your interview. Good luck and I'll see you in the next video. Until then, it's bye bye from Vasant Shanmugam and your favorite Little Slaw YouTube channel. Take care and bye bye. Hi, hello, vanakkam, and welcome back to yet another episode on your favorite Little Slaw YouTube channel. So today we are going to focus on something that separates engineers from great ones. So I'm starting from the very beginning because this is going to be very quick technical interview session. It's going to be again a kind of an interview session again. So where we're going to see about the production debugging skills, and specifically we're going to talk about concurrency issues and thread dump analysis. So this is very critical for us because our platforms, they always handle high frequency trading systems where the performance and reliability are non-negotiable. So before I dive in, let me give you some context. So this is a kind of a scenario where you could get a question like this. So we have a production incident. So we had a production incident at around 3 a.m. On, take for example, Monday or Tuesday, and our trading platform, like the platform that we use, has completely got froze, right? And Yep, I think, yeah, this is here. So how do you identify deadlocks in a thread dump? So again, as I told you, at around morning 3 a.m., uh, there was an incident and the platform got froze. So there are like no crashes or no errors in the logs, just it got frozen, okay, which is like completely unresponsive. And we had clients or we had users on the phone who are like screaming because millions of dollars were at stake, right? Because if they are not able to use the application, then automatically that could happen, and people around the globe is using that application. So the engineers are capturing the thread dump and they have to analyze it. So, and they have to quickly identify the root cause because, as you can understand, this is a kind of a production issue. So this is a kind of a scenario where they don't just expect just the theoretical knowledge. You need to have hands-on, some debugging experience. So the question is, I want to hear from you about the complete thought process. So I'm not looking for a textbook answer. All I want to know is how would you actually debug this in production, and what tools you would use and what you would look for. And most importantly, how would you identify the problem quickly when the pressure is on, right? So let me ask you the question, and after that, we'll go and see the answer. So this is the one that in slide 2 that you see here. That is um, the scenario, the actual scenario. So you get an alarm or you get an alert at 3 in the morning. That's the application is completely frozen. Users cannot log in. The transactions are not processing, but the JVM is still running. And the CPU usage is at like around 5%. So it's not running anyway. And it's not a runaway loop. And the memory looks fine. The application just is not doing anything. So you SSH into your production server and you capture the thread dump using JStack. And now you have got this massive text file, maybe like 5,000 lines, and that could be the actual production thread dump of thread information. So the question is, how do you identify deadlocks in that thread dump? So in that thread dump, when I say the massive text file with like 5,000 lines, so it's not just like one pager where you can go and do something, right? So you have to be specific about what you're looking for. So now the answer is, so this is how your answer should be. So you should be very specific of what you're looking for. And the interviewer would want to know about the JVM's built-in deadlock detection. So what does it actually report and where do you find it? And second, if for some reason the JVM does not explicitly report a deadlock, so how would you manually analyze the thread dump to identify one, and what are the indicators and what patterns are you looking for? And thirdly, this is important. So what tools would you use to make this analysis faster? Because in production, the speed matters, because people behind you are like bugging you because nothing is working. So in production, it's the issues in production and you have to like do something real quick. So you can't spend 30 minutes reading through the thread dumps when the readers are, or when the users are losing their money every single second. And on top of that, just to give you more context, so this is a multi-threaded application. So we have got maybe around like 100 threads running at any given time. And the database connection pool threads, the HTTP request handler threads, the background job processes, scheduled tasks, the WebSocket connections, everything works, right? So it's a real production application, not just a pet store application, right? Pet store example. So we have to walk through, or we have to do a walkthrough. So like how do you find the deadlock and what's the systematic approach? So we've got like around 90 seconds maybe to explain, right? So let's move to the slide 3. So how will be the response, right? So let's break down the approach into 3 parts. Firstly, the easy path using JVM's built-in detection, and secondly, manual analysis. So when we need to dig deeper, and thirdly, the tools and techniques that makes this faster in production. So starting with the JVM's built-in detection, deadlock detection, that is actually the first thing which we must always check, because the JVM does most of the work for us. So when we run the JStack on a JVM process, if there is a deadlock, the JVM explicitly reports it. So we will see a section in the thread dump that says, and I'm quoting here, if you found one Java level deadlock, which is followed by a row of equal signs, and that's the JVM telling you, hey, I detected a deadlock and here's what's been involved. So what's great about this is the JVM does not tell you that there is a deadlock. It actually traces the circular dependency for you. So it will say something like thread A is waiting to lock monitor 0x0, whatever the number is, which is held by thread B. And thread B is waiting to lock monitor again with the number which is held by thread A. So it gives you the complete cycle now, right? Because I mean, thread A is waiting for thread B is waiting to lock the monitor which is held by thread A. So this is by far the fastest way to identify deadlock. And if you see that message, you're done with identification. So you have found your problem. Now you just need to look at what those threads are actually doing and fix the code. That's the first thing. And then let's talk about what we see in that report. So each deadlocked thread gets listed with its full name. So like HTTP, NIO, 8080 with the port number, executive, and then the number like 47 or 48 or whatever number is, or like pool 3 thread 12 or whatever the number, or whatever your multi-threaded naming convention is. So we get the thread ID, we get the thread state, which will be blocked, and you get the lock information. So the lock information is very critical because it shows you the monitor address in hexadecimal, like you see in the screen here. The object reference that's been locked. So usually something like java.lang.object or com.yourcompany.some class, so whatever the class is, and which other thread currently holds that lock. So the JVM is basically drawing you a diagram, and here's the chain. Thread 1 needs what thread 2 has, and thread 2 needs what thread 1 has, and that's what we call as deadlock, right? And moving on to the next slide. So sometimes the JVM's automatic detection does not catch everything, or sometimes we are dealing with a distributed deadlock across multiple systems, not just thread A, thread B, thread B to thread A. So we need to know how to manually analyze the thread dump. So here is what I look for. So first indicator is blocked threads. So I grep for the word blocked. So grep is something search command which we use in Linux, a Unix environment. So we search for that word blocked in the thread dump. And if I see a bunch of threads in the blocked state, and that's a red flag. So a few blocked thread is normal in any concurrent system, but if you have got 10, 20, 30 threads all blocked, something is definitely wrong. And secondly, I look at what those blocked threads are waiting on. So in the thread dump, you will see a line that says waiting to lock, followed by a monitor address, as you see here, like you see here, and an object reference. And that tells you this thread wants to acquire this lock, but you can't because someone else has it. Thirdly, and this is the key to finding the deadlocks manually. So I trace, or we should trace the lock ownership chain. Let's say thread A is waiting to lock monitor 0x, whatever the number is. So you must search the thread dump for the monitor address. So you should, you must find the thread B, or you should search for thread B, and you must see that thread B must be currently holding that lock. So thread A is waiting for thread B. So this is what you're going to find it manually. But then you must check what is this thread B waiting for. And this is where you find the cycle. So thread B is also blocked, which is waiting to lock monitor 0x5678, the number which you're seeing here in the screen. So you search for that monitor and you find it's been held by thread A. So there is a circular dependency, and that's your deadlock. So in practice, this manual process takes maybe 2 to 3 minutes if you know what you're doing. So you're doing a lot of searching through the file, you're cross-referencing the monitor addresses, building a mental model of the log graph. So just to summarize the key indicators, so blocked thread states, waiting to lock messages, and circular references in the lock ownership chain. So if thread A needs thread B's lock and thread B needs thread A's lock, that's a classic 2-thread deadlock, but you can also have thread 3-thread or 4-thread deadlocks. A waits for B, B waits for C, C waits for A. So same principle, but a longer chain. So the monitor addresses are your breadcrumbs. So you have to always look for the monitor addresses. So follow them and you will find the cycle. And moving on to the slide 5. So let's now talk about tools, because doing this manually at Just imagine at 3 a.m. is really painful and stressful. So first, JStack itself. I always use JStack minus L with the lowercase L flag. So the L stands for long format and it gives me additional log information that can be helpful. The basic JStack output is usually enough, but the long format gives me more details about logged synchronizers and can help me spot issues faster. But honestly, for production debugging, I don't read raw thread dumps if I can avoid it. I use analysis tools and my go-to is fastthread.io. So you upload your thread dump and it gives you a visual analysis. So it automatically detects deadlocks, highlights blocked threads, shows you CPU consuming threads and gives you a nice graphical representation of the log dependencies. It's free and it's fast. And next, another tool which is Visual VM's thread analyzer. So if you can connect Visual VM to the running JVM, which you can't always do in production, so it gives you real-time thread visualization. So you can see deadlocks as they happen, which is incredibly useful for reproducing issues in staging. And Eclipse Mat, which is also great. It's primarily for heap dump analysis, but it can process thread dumps too, and it's good at finding complex log patterns. And JConsole is built into the JDK and can connect to a running JVM and it detects deadlocks in real time. It's simple but effective. And for command line fans like me, I often grep the thread dump. So grep found dot start deadlock will jump straight to any deadlock reports, and grep blocked shows all blocked threads. So you can pipe these together with AWK and SED to build quick analysis scripts. So now here's something really important that you must mention, that you have mentioned earlier. So this is relevant to the performance testing aspect. So deadlocks often only surface under high concurrency, right? So in development with one user, you might never hit them. But in production with hundreds of concurrent requests, the race condition aligned just right. And yes, deadlock. So this is why load testing is absolutely critical. So I always run high concurrency load test before major deployments, specifically to try to trigger race conditions and deadlocks. So tools like JMeter or Gatling running thousands of concurrent threads will expose these issues. So you capture thread dumps during load test, analyze them and catch deadlocks before they hit production. In production, I always also have automated monitoring JMX beans that can detect deadlocks programmatically, and you can set up alerts. So if a deadlock occurs, it triggers a page duty alert and automatically it captures a thread dump and notifies the team. So you don't want to wait for users to report that the system is frozen. And then finally, the last slide. So these are the actual responses that you must give. So from a technical knowledge perspective, you must score. You must have a clear understanding of the JVM internals, the thread states and lock mechanisms. So the way you explain it to the interviewer in terms of the monitor addresses and the lock ownership chain, and that will show your deep understanding and not just surface level knowledge. So you have obviously done this in production, not just read that in the book. So you must also mention the specific JStack flag, that's minus L, the lowercase L for long format. So that's a detail that will show that you have actually used that tool, and your explanation of how the JVM report deadlock was spot on. And that found one Java level deadlock message is exactly what you must see for, and you quoted it, and you must really quote it. In terms of debugging skills, you must explain the complete process of tracing the lock graph manually. So that's important because sometimes the JVM does not catch every deadlock scenario, especially with higher level concurrency utilities or distributed locks. And the three-step approach that you must explain, which you use to check JVM's automatic detection, manually analyze if needed, and using tools to speed it up. And that's exactly the right methodology. And that will show that you have debugged real production issues where you need to be both thorough and fast. And finally, you must be very clear, very structured. So you have to break down complex topic into digestible parts, and you have to give concrete examples with specific thread names and monitor addresses, which made it easy to visualize to the interviewer. So overall, you must demonstrate excellent debugging skills, your deep JVM knowledge and production experience. And this is exactly the kind of engineer that they would expect for the team. Someone who can handle a 3 a.m. production crisis calmly and systematically. So with that, I think I come to the end of this video. Um, until I see you all in our next video, it's bye bye from Vasan Shanmugam and your favorite Little Sla YouTube channel. Take care and bye bye. Hi, hello, vanakkam, and welcome back to yet another episode on your favorite Little Sla YouTube channel. So today we are going to see about the question that is, what is thread contention and how does it appear in thread dumps? So this is again a very straightforward question, but the interviewer would want to hear your complete understanding. Again, not just the textbook definition. So the interviewer must want to know that how would you actually diagnose this in production and what you would look for in the thread dump. So let me give you some context. And again, before that, let me reiterate the question. So what is a thread contention and how does it appear in thread dumps? So talking about the context, this is actually a real-time scenario where the API response times went from 50 milliseconds to 5 seconds and no code deployments, no infrastructure changes, right? So we captured a thread dump and it was immediately obvious what the problem was. It is like severe thread contention. So specifically, the interviewer would want you to explain want him to explain that what is thread contention and how would you identify that in a thread dump and what are the common causes and how would you approach fixing it. So to be very clear, the interviewer is not asking you about deadlocks. That's different. And here he's asking about the contention, like whether threads are competing for the same resource. It's not a kind of a circular dependency. It's more like a traffic jam where everyone is trying to get through the same narrow gate, right? So moving on to the slide 3. So again, this is actually a very great question. Thread contention is exactly what we described. So it's when multiple threads are competing for the same lock or resource, but they end up waiting in line for access. So think of it like a single bathroom at a concert, and everyone needs to use it, but only one person can be inside at a time. So you get a long queue of people waiting. That is contention, right? That's not deadlock. So don't confuse deadlock with contention. In thread terms, you have many threads that all want to execute the same synchronized block or access the same locked resource, but only one can hold the lock at any given time. So in a thread dump, contention is really obvious because once you know what to look for, and you will see a large number of threads in the blocked state, and critically, they are all waiting on the same monitor address. For example, you might see 20 threads all with waiting to lock followed by the same hexadecimal monitor address, like waiting to lock followed by that monitor address, and then you will find that one thread in runnable state that currently owns that lock, and that's the bottleneck. Yeah, so one thread is doing work while 20 others are just sitting there waiting for their turn. So the key indicator is repetition. So if you see the same monitor address appearing over and over in different thread stack traces, and that's contention. So the more threads waiting on the same lock, the worse the contention. So moving on to the answer part 2. So now what causes contention? So most commonly it's synchronized blocks that are too coarse grained. So developers will wrap a large chunk of code in a synchronized block and that code might take half a second to execute. So during that half second, every other thread that needs that same lock is blocked and waiting. And another classic cause is database connection pool exhaustion. So you have got a pool of say 10 database connections, but you have 50 threads all trying to get a connection at the same time, and 40 threads end up waiting, and you see massive contention on the connection pool's internal logs. And thirdly, the common cause is single threaded bottlenecks. In other words, multi-threaded code. So for example, you might have a singleton service that all your request handlers need to access, and it's protected by a single lock. So even though you have got 100 request handling threads, they all bottleneck on that one service. So I have seen this with logging. So some puts a synchronized block around the logging code and suddenly every thread in the application is contending on the logger. It seems harmless because logging is fast, right? But when you have high throughput, even fast operations become bottlenecks when they are synchronized. So the key pattern here is critical sections that are too large, too frequent, or both. So moving on to the third part of the answer. So to analyze contention in a thread dump, I start by counting the blocked threads. So if I see more than like 10% of threads blocked, that's a warning sign. That's a red symbol. Then I group them by what they are waiting on, and I'll use grep. Grep again, it's a very common, very useful command or a thread dump analyzer to count how many threads are waiting on each monitor address. So the monitor with the most waiters is your primary bottleneck. Then I look at the thread that owns that log. So what is it actually doing? Is it running a slow query, or is it making an external API call, or is it expensive? Is it doing expensive computation? So that tells me why the contention exists. So for resolution, it depends on the cost. So it's if it is coarse grained locking, I reduce the log scope and only synchronize the smallest critical section necessary. So if it's a database connection pool, I increase the pool size, but also investigate why we are holding connection so long. So often, the best solution is to move away from synchronized blocks entirely by using concurrent collections like concurrent hash map instead of synchronizing on a hash map. So use atomic variables instead of synchronizing primitive updates, and considering log-free algorithms or message passing if appropriate. And sometimes the answer is asynchronous processing. Yes. So if the threads are waiting for input output, don't make them block. Use async operations and callbacks. That frees up threads to do other work while waiting. And finally, the last way where you will get evaluated based on whatever we have given as an answer to the interviewer. So in overall, I would say that you must demonstrate the understanding, a solid understanding of how concurrency, performance issues, and the practical debugging skills and your good problem solving skill instincts. So it's always good that you demo or you showcase all your knowledge on this part. So with that, I come to the end of this video. I think I've shared you the difference between what is a thread dump and what is a contention here very clearly. So we'll meet in another interesting video. Until then, it's bye bye from Asan Shanmugam and favorite little Salah YouTube channel. Take care and bye bye.